Hello everyone. Today we're going to tackle the 1990 AIME Problem 5. So here's the problem. Let n be the smallest positive integer that is a multiple of 75 and has exactly 75 positive integral divisors, including one in itself. Find n over 75. So the key idea for this problem is that it is a number theory problem because it involves divisors, divisibility, like n is divisible by 75, etc. And like I said, it involves some divisor techniques. So the first thing we notice is that n is a multiple of 75. So what does this mean? Divisibility for 75 is divisibility for 3 and 25. So what is the formula for divisibility for 3? You should know that from primary school. So for divisibility by 3, if the sum of the digits of the number is divisible by 3, so the entire number would be divisible by 3. And for divisibility for 25, the last two digits must be divisible by 25. Just like for divisibility for 5, the last digit must be 5 or 0, so it would be divisible by 5, the last digit. So now we focus on the 75 positive integral divisors, including one and itself. This is the key thing for the problem that we need to solve. So the formula for finding the number of positive integral divisors is this formula. For an integer, and suppose that its prime factorization is n equals p1 exponent e1 times p2 exponent e2, etc. So the number of divisors formula would be each exponent added by 1 and multiplied together. So it's e1 plus 1 times e2 plus 1 times ... until em plus 1. So from this point, we need to try to find n, because this is the key to this problem. We need to find n over 75, so we need to find n. So because n is a multiple of 75, n must have factors 3 and 5, because 75 is equal to 3 times 5 squared. So if n is divisible by 75, n must be divisible by 3 and 25, just like what we saw in the last slide. So now we have n equals 3 exponent e1 times 5 exponent e2. So now we see that n must be the smallest positive integer. So we need 75 divisors. So by the formula for the number of divisors, we have e1 plus 1 times e2 plus 1 equals 75. And now how do we proceed? Because e1 plus 1 is always a positive integer, and e2 plus 1 is also always a positive integer. So we can consider factoring 75 into 3 times 5 times 5. And we need to distribute these factors to each of these e1 plus 1 and e2 plus 2. So now we have two possibilities. So either e1 plus 1 equals 15 and e2 plus 1 equals 5, or e1 plus 1 equals 3 and e2 plus 1 equals 25. And we can switch these. So 15 and 5 can be 5 and 15, and vice versa. Now the big problem is that n would be way too big if we use this calculation. Because imagine if we take 15 and 5 as an example, and we set e1 plus 1 equals 15 and e2 plus 1 equals 5, we would get e1 equals 14 and e2 minus 4, because 15 minus 1 equals 14 and 5 minus 1 equals 4. And the problem is that n over 75 would be this 3 over 3 exponent 13 times 5 exponent 2, and that would be way too big for the AIME, because AIME problems have answers from 0 to 999. And 999 is the biggest number that it's possible, but 3 exponent 13 would certainly be bigger than 999, so it wouldn't fit. So now we're stuck. So now we should seek for something else. How about adding factors of 2? Why considering factors of 2? Because in the last slide we considered only factors of 3 and 5. And if we only consider them, the big problem would be that n would be way too big. But we want the smallest n possible. So why wouldn't we take some factors of 2? It's totally legal to do that, because 2 is smaller than 3 and 5. And 2 is not considered 1, because 1 is not a legal factor. So now we would have n equals 2 exponent e1 times 3 exponent e2 times 5 exponent e3 to reduce n. And we have at the right e1 plus 1 times e2 plus 2 times e3 plus 1 equals 75, just as what we have seen in the last slide. So recall that 75 equals 3 times 5 times 5. And now what we need is to plug every factor into every ei plus 1. So to minimize n, we should have more factors of 2 and less factors of 5. Because if we multiply more 5s, n would be bigger. And the other way, if we multiply more 2s, n would be smaller. So we need to put e1 equals 5, e1 plus 1 equals 5, e2 plus 1 equals 5, and e3 plus 1 equals 3. And we get e1 equals 4, e2 equals 4, and e3 equals 2. So now we're basically done. So n equals 2 exponent 4 times 3 exponent 4 times 5 exponent 2. And we're sure that the number of factors would be 75 by the number of factors formula. So now we're actually almost done. But wait, we need to have n over 75, not n. We need to pay attention to what we need to find. So we have n over 75 equals 432. So the answer is 432. So what should we take away from this problem? Take all the information given in the problem. So as we focused in this problem, I highlighted several parts of the problem in every slide to focus on what we need to think about, like the multiples of 75. It can be factored into 3 times 5 over 2, or like the number of divisors formula, etc. And know your formulas. Here we talked about only the number of divisors formula and how do we determine the divisibility by 3 and other stuff. But you need to know your formula to solve a problem. It's a key to success. And think for several ways to tackle the problem. Do not get stuck for a long time on one direction. Why? Because when we considered e1 plus 1 times e2 plus 1 equals 75, we only had factors of 3 and factors of 5. And we didn't consider any factors of 2. And when we're stuck, we need to think about other ways to solve this problem, because we cannot be stuck in one way, and we need to think about other ways to solve the problems. So here's again the formula for the prime factorization, the number of divisors formula. So thank you for listening, and this problem is very nice because it's a number theory problem and it involves divisibility. So thank you for listening again, and see you soon.